next speaker for our session today. So we will have the topic about designing YDB, constructing a distributed database management system for OLTP and OLAP from the ground up. And the speaker will be Eugene. He is the principal software engineering at YDB, and his favorite ice cream flavor is chocolate. So ladies and gentlemen, please give him a warm welcome. It's your day now, Eugene.
Thank you, Wendy. Sawadee Krap. So we are going to speak about distributed systems, about OLTP and OLAP. Again, my name is Eugene, and I am developer at YDB. I'm a really massive fan of distributed systems and databases, and it's best when they are combined together like in YDB. First of all, I would like to make a very important disclaimer. There are many rumors about YDB and Yuga YDB. Some people say we had a bar fight. Other people believe we are exactly the same systems. Also, it's possible to be exactly the same system and have a bar fight, if you remember classic movie. And today is the time for truth. Actually, we are different distributed database management systems. We are both developed by absolutely different companies, by different people. But we are we are friends with Yuga YDB, and we enjoy discussing distributed database systems, benchmarks, etc. So if you are from Yuga Byte, hi guys. Well, to the topic. Actually, YDB is not just a distributed database. Actually, it's a platform because we support OLTP, OLAP, even we have Kafka-like persistent queue. Moreover, we have AC transactions between topics and OLTP tables. It really simplifies application development. Besides that, we also have more stuff. You might want to check our website. We have stuff like NBS, Network Block Store, for example. And we are fully open source. That's why we are here. We are a relational database, so we have SQL. And we are a major system. It's 10 years of development. We have huge clusters with thousands of servers. Really petabytes of data. And feel free to start our database on GitHub. We really love, we would really appreciate if you start us on GitHub. We are strictly consistent. In case of partitioning, we choose consistency over availability. So we choose actually CP, which is very important for application development and for important data. We have serializable transactions. It simplifies application development a lot. It makes us mission-critical database for mission-critical data. Consider example. You have a 3 availability zone setup. Availability zone is usually a data center. And one data center might be in fire. Another data center might be partially flooded. And in this case, YDB is still read-write available. And actually, it's not just a theoretical example. It's actually from practice. It might happen. And if you want your database to be available, you should choose distributed solution because otherwise you would lose a lot of money. So we have no downtime for releases because of our architecture, and we work the whole year without maintenance. There is a fun fact about YDB. There are clouds based on YDB. They use YDB for their metadata. And some of these clouds implement their network block store using YDB as well. Network block store, it's analogous to EBS in Amazon. And some of these clouds provide YDB as a service. And that's make YDB bootstrappable. And if you buy this YDB as a service, you get YDB over YDB over YDB. Now, let's jump to main topic and have a quick overview of our functionality. As expected from any relation database, we have tables. Each table has primary key, and data is sorted by its primary key. And we split all the data into ranges by its primary key. We have SQL, we have transactions. Everything is stored in table. And here is a picture showing our architecture. At the bottom, we have distributed storage. And distributed storage is responsible for data replication. For example, it might be pure replication, or it might be some other stuff like, I will talk about it a bit later, like redundancy schemes, like erasure coding. Above, we have tablet layer. Each tablet contains actually user's data. And we have distributed transactions over these tablets. And above, we have, of course, query processing, because we have SQL, we have gRPC layer, and users interact with YDB using our SDK through the network. Today, we are focusing on platform components, distributed storage, and tablets. So let me tell you, but before, let me tell a little bit more about our logical and physical organization. First of all, we have storage and compute completely separate. It allows to scale them completely independently. So you can, depending on your workload, you can scale your storage, or you can scale your compute. In case of storage, it's just distributed storage with few very special tablets. But in case of compute, it contains distributed transactions, query processing, and a lot of other stuff. And if your tablet dies, YDB infrastructure is responsible to restart your compute automatically in proper state. You can easily run YDB anywhere. It can be bare metal, it can be Kubernetes, it can be cloud. So YDB can be run anywhere you need. Typical YDB cluster has shared distributed storage with multiple dedicated databases. So dedicated databases are compute, and compute is separated. And sometimes you would like to share storage between multiple compute because it's more resource efficient. But sometimes you need serverless solution. In this case, single dedicated database is shared between multiple serverless databases. So it's up to you what you actually need. Now it's time to discuss distributed storage. Distributed storage is a very special purpose storage. It's key value storage. Key I will discuss later, and as a value we use blobs. Also because this distributed storage stores blobs, it's historically was called blob storage, and because I'm an old guy, sometimes I call it not distributed storage, but blob storage. I use this interchangeably. And blobs are from 1 byte to 10 megabytes. But it's transparent to users. It's automatically cut into pieces. So distributed storage is dramatically optimized for log. So it's optimized for log records because sometimes, especially in OLTP, you have a lot of transactions and they write data, and each transaction has to write data to be actually serializable. We support multiple redundancy schemes. It might be, if you have single availability zone, it might be erasure coding. In this case, you have redundancy 1.5, which is really cool if you out of disks. So if you don't have too many disks, it's a nice scheme. But if you have 3 availability zones, I mean, it's mostly when your data is very, very important. We have replication, and redundancy is x3. But actually, we support more schemes, and you can easily extend our distributed storage, adding even more schemes. Well, what do I mean by special purpose? Because it's just key value storage, why is it special purpose? Few IP calls are really straightforward, like put and get, but there are few very special ones. There is a call called block, and it's used for distributed consensus. So when, also I can say, you could say that it's for leader election. When tablet wants to become a leader, it uses block IP call to get the quorum from distributed storage. So here we have a consensus. It's similar to multi-paxes. And we have also a very, very special call, collect garbage. We have a barrier-based garbage collection. So tablets are responsible to tell when and how to move this barrier to collect unused blobs. And each distribute node looks like this one. There are devices, and each device is controlled by a single entity called pdisk. We don't have file system between YDB and disks. We control disks on our own because we would like to implement special optimizations. And also we have fair scheduler because above pdisk you have multiple virtual disks. And we would like to control bandwidths allocated to each disk. We want a fair scheduling. And usually each pdisk really can have multiple virtual disks. So virtual disk is unreliable component, but we form a group of virtual disks, and each group now is a reliable component and fault tolerant one. And our distributed or blob storage consists of many such groups. And you can think about distributed storage. I think it's the best way to think about our distributed storage as distributed rate. Tablets are connected to these blob storage groups. They use these blob storage groups as a reliable storage for their data. And actually, there is a special entity called DS proxy. DS proxy is aware about structure of the disks. It knows which disks it should use. And it's responsible for failure, to handle failures of network and virtual disks. So it's for tablet, it's really easy to communicate with virtual disks because there is a special entity and it simplifies life a lot. And API is quite straightforward. The disk is actually an active component. Because there is synchronization between disks of same group. For example, if you get a temporary failure, so for example, your server might be down for some time, it might move somewhere, and when virtual disk is online again, it will go to its neighbors in the group and automatically replicate. Let's look on blob storage group and how reconfiguration might be done. We don't have static configuration, we have dynamic configuration. So if you have some changes in your data center or within your cloud, you can easily move virtual disks from one location to another one. Also, in case of failure, for example, your disk might die. It can be easily damaged. Even modern disks usually die after some time of operating. Recovery can be done fully automatically. So the system is responsible, in this case, YDB is responsible for moving YDB from bad node, from bad disk, to move from bad physical disk. It moves virtual disks to good disks to keep system running. And distributed storage users, they are completely isolated. So you have two levels of isolation. You have isolation on compute level. In this case, no hardware is shared between compute nodes. It's a separate operating system process. But usually they share same distributed storage. They don't share groups. They have different groups. But groups might share same hardware. And depending on your needs, you might set up this because it's resource efficient, or you might want to set another type of installation when you have no hardware shared at all. So it depends on your failure model. Distributed storage is really fault tolerance. Devices can be broken, they can be replaced. We have self-heal, I have mentioned it already, so special process is responsible for healing your cluster. And It's scalable. And because it's completely separated and you have multiple groups, you can easily add more disks, more servers, and you can scale storage completely independently from compute. And we actually have installations with thousands of disks, even more, with thousands of servers, and each server has usually many disks, so it's maybe tens thousands of disks within a cluster. And we checked that our special tablet blob storage controller, it easily handles 10K storage nodes. And each storage node might contain multiple P disks and a lot of V disks. So let's jump to tablets. I'm sorry, it doesn't seem. Okay, YDB tablet is actually, it's stateful, and it's actually reliable stateful building block. So actually it's replicated state machine, RSM. Probably you might know that RSM is usually a part of any distributed system. And tablet is a place where you implement user's logic, like storage or columnar storage. And YDB tablets, they run in compute nodes. Let's look on the picture. Tablet encapsulates user logic, like columnar or store, and it has own database implemented over blob storage group. Actually, there is LSM. Usually, LSM is actually what is used with replicated state machine, and it uses blob storage to store two kinds of data. Tablet log, because you need it when you restore tablet on another machine or after a start, and blobs corresponding to log structured merge tree to LSM. And distributed storage provides a really reliable way to store a tablet's data. It's really easy to add new type of tablets. Actually, we don't have just columnar store and row store. We have key value tablet, which is part of our SAM project, and so on. Each tablet has multiple channels. At least it has system channel for its log, and it has channels which depend on the way you use data. For example, you might have SSDs and rotating disks. Rotating disks are slow but cheap, and you would like to store some columns on rotating disks because these columns are rarely used, and you might want to store hot data on SSDs. It's impossible to configure a table in a way that rotating disks are allocated to rarely used columns, and SSDs are allocated to columns which you often use. And finally, let me briefly describe again some tablet types. So data shard, I mentioned it a lot today. It's a row store. It supports SQL transactions. It's ACID, it supports SQL transactions. Transactions are serializable. We have columnar store. It's used for analytical workloads. We have scheme shard. Scheme shard is used to store scheme metadata of your tables. We have a very special system tablet called Hive. Hive is responsible for starting all the tablets for balancing cluster. Actually, if you have questions about balancing, maintaining tablets, we have a core developer of Hive here today. So he's sitting even he's sitting right here in this hall. Feel free to ask questions later. We have coordinators, mediators, because we originally were based on Kelvin IDS, but we seriously extended Kelvin IDS. And we have cluster management systems. Of course, there is a place for configuration. And finally, we have some sort of sysview processor. It contains some statistics. You might want to use it to optimize your transactions. And unfortunately, there is no information on the slide, but as I mentioned, we have topics. It's also a special tablet. And if you are interested in topics, there will be another YDB talk on Friday at 10. It will be about AI, about RAG, topics, streaming, vector search. Feel free to listen to my colleagues about these fascinating topics. So thank you a lot for your attention. There is QR code on our website. Feel free to hit me up with questions now or today or all these days. Our booth is actually located right opposite to the hall number 2. Thank you so much for your attention.
Thank you so much, Eugene. We still have time for 1 to 2 questions. So anyone want to have any question? All right.
I have a small question. I mean, I have many questions.
Let's go outside.
I'm just going to ask one, because I've been working on OLAP multi-cluster applications, and you've mentioned one slide ago something called the transaction allocator. If you scale your system across multiple shards, many nodes, I mean, you're using that, I guess, I'm not familiar with your architecture, so please correct me, to ensure ACID properties across multiple nodes. Don't you have a scalability problem when you use that, depending on the number of nodes you have, because you want to maintain a global visibility of your data, which I guess is repeatable read or read committed, repeatable read or read committed, not serializable. So isn't your transaction allocator potentially a scalability issue? How much do you use a transaction allocator for how many nodes? Or, I mean, isn't it a single point of contention? Or
Thank you very much. That's a very interesting question. First of all, if we speak about OLTP, we have either serializable transactions or transactions which are repeatable read. It's if you can choose between serializable level of isolation, it's by default, and you can use if you want to read from followers, you can get stale read, so it's snapshot isolation, it's repeatable read. In case of serializable isolation, we have multiple coordinators, and we have multiple mediators. So if you definitely, if you have a single coordinator, it might be a bottleneck. But it's possible to shard coordination between multiple entities. And also when you have to send your coordination decision, you might use another level of abstraction called mediators. So we solve the issue of single bottleneck with coordinator by using some special smart sharding of coordination. In case of in OLTP, you also can do scans, but it's not. I think you don't want to use serializable snapshot isolation because you will get logs invalidated if it's really long transaction and you have writes. But you can easily use repeatable read in this case. You can get some stale data, but it will be okay. In case of OLAP, to the extent of my knowledge, it's repeatable read only. OLAP, our OLAP support is not serializable, but at least to the extent of my knowledge. And I don't think there are systems with OLAP workloads which are actually serializable. But if you have many questions, please reach me.
I have much more questions, actually, 10 times more questions now.
Yeah, okay, you can reach me outside. I have also my colleagues, and we can discuss it deeply. That would be nice. But thank you for a very interesting question.
So the applications running on YDB, who has the owners, right? Is it the applications or the database which is giving you the nearest node?
It's up to you. You can run application anywhere. If I understand your question correctly, you have endpoint to your database, and applications use our SDK to connect to the database. We have partial Postgres compatibility, so you can use even PSQL CLI, and it connects to YDB the same way as to Postgres.
You mentioned that the primary keys are used, stored in ranges. How do you store indices? What's the storage for indices?
Well, actually, indices are implemented exactly the same way as regular data, but they are more dense or spare. I don't remember correct word. So indices implemented exactly the same way. It's a tablet, very similar to data shard tablet. And it's up to scheme shard to get information about indices, about shard location, and query processor is responsible for choosing proper shards. So when you have a query involving index, query processing goes to scheme shard. If we don't delve into the details too much, it gets information about sharding of data and about indices. And then it goes to proper shard, which is just same key value table with some structure.
All right. Because we are run out of time now, so really want to say thank you for all the sharing today, Eugene, and thanks a lot for all of the questions from you.